In this video, we will start our review of basic semiconductor concepts. There are plenty of concepts to cover, so all we can do in this class is to cover them very briefly without much explanation, because this is not part of the main MOS transistor course. The entire course will be based on a few facts that we will cover in this video and the next several videos. A deep understanding of these facts requires familiarity with quantum mechanics, thermodynamics, and solid-state physics. Of course, we will not assume such familiarity in this class. Instead, we will simply mention those facts. You would have to take them for granted, but I will try to make them plausible for you. Let me first state the assumptions that we will assume to be valid unless we say otherwise. We will assume that there is no illumination, no radiation, no external electric or magnetic fields, and the semiconductor we are considering is assumed to be at a single temperature throughout, and the default will be 300 degrees Kelvin or room temperature. If in addition there is no exchange of energy with the external world, and if there is any disturbance, we have waited long enough for this disturbance to have disappeared, and we are in the so-called settled state, then we say that the semiconductor is in equilibrium. And this will be assumed unless we state otherwise. In particular, in equilibrium, there is no electric current. So let us start our discussion of intrinsic semiconductors, where intrinsic means that there are no impurities in them. Later on, we will add impurities. We assume we are in equilibrium and at room temperature. So here is a two-dimensional simplified structure of what is actually a three-dimensional situation in a piece of semiconductor. We have silicon atoms. Here you see one atom, here you see another atom. Each of them consists of a nucleus and electrons. Of all of the electrons, we only show 4 here, and these are the outer shell electrons that are responsible for forming covalent bonds between the atoms. For example, this is one covalent bond between these two atoms. Here is another one, and so on. The black dots are electrons, and each of them carries one electron charge. They are negatively charged, so their total charge is -4 electronic charges. Because the atom is overall neutral, that means that the rest of the atom, as shown in the big circle here, has a charge of +4. So the overall charge of each atom is 0. Here you see the so-called energy band model of the semiconductor. The vertical dimension here is electron energy, and the horizontal dimension is distance along the semiconductor. The electrons that participate in valence bonds have energies inside this valence band. At 0 absolute temperature, things are not moving, as you know, and all of the electrons are frozen, so to speak, inside their valence bonds. If you increase the temperature, thermal agitation in the crystal lattice starts, and sometimes it imparts enough energy to make an electron jump all the way from the valence band to the conduction band. This means that now the electron is free to leave the covalent bond and to wander around the crystal lattice. So for example, let's say this electron here moves out like this. So keep in mind the symbols here. E sub B is the top of the valence band. E sub C is the bottom of the conduction band. And E sub G is the energy gap, which is about 1.1 electron volts. Now, once this electron got enough energy to get into the conduction band, it is free to move, as you see here. And what happens is it leaves behind a vacancy shown by an open circle over here. This vacancy is called a hole. Because the atom was overall neutral before, now that one electron has left, the overall atom is left with a positive charge. And so we say that a hole is positively charged, just to associate the two together. Now, this hole is not free, just like this electron is not free. But another electron from another atom here can move into this hole and fill it in, like this. And what happens is, once this happens, this covalent bond will be repaired, but now there will be a hole over here. So that's equivalent to having this valence bond, covalent bond intact, and now the hole has moved here. And therefore, you can see that rather than saying that bound electrons move from bond to bond, it's equivalent to saying that hole moves in the opposite direction. We see that the hole is available to move. And it happens, although we cannot explain it in simple terms, that just like electrons are free to move here, holes are free to move in the structure. Now, electrons carry a negative charge, holes carry a positive charge. The detailed picture I showed you here will not be relevant to our discussions to a large extent, so instead we provide this very simple picture. There are free electrons, just like this one, which are shown here. All of these are free to move. And there are free holes, which have positive charges, and they also are free to move. Each electron corresponds to one hole, so the number of holes and electrons is the same. The concentration of electrons per unit volume will be denoted by N. The concentration of holes is denoted by P, and the two are equal. So in the intrinsic semiconductor, these concentrations will be denoted with a little I subscript. And the product of the two, of course, will be Ni squared, as you can see from here. So the product of N and P is equal to Ni squared. And to give you some idea, Ni is approximately 10 to the 10th electron or hole carriers per cubic centimeter. Now, this actually corresponds to a very, very small number if you compare to the number of atoms in the lattice. The number of atoms in the lattice is about 5 times 10 to the 22nd per cubic centimeter, which means that you actually get one whole electron pair per, or less than one whole electron pair per 1 trillion of atoms. Yet this minute concentration is enough to give you conduction. Let us now talk about extrinsic semiconductors. These are semiconductors into which dopants have been inserted, impurities. Again, I'm assuming thermal equilibrium and room temperature, and I will assume non-degenerate, in other words, not very heavily doped semiconductors in this discussion. So I start with the so-called N-type semiconductors. These are called actually donors because they will donate 1 electron each to the silicon structure. Examples are phosphorus, arsenic, and antimony. These have 5 valence electrons. Here I show you 1. 4 of these valence electrons form covalent bonds with the rest of the structure, and 1 of them is free to move. This electron has been donated by this atom. So basically each of these atoms, if it is, as we say, ionized, donates 1 electron to the structure. The energy band picture for this N-type semiconductor looks like this. This here corresponds to the energy of the electrons in the dopant atoms. As you can see, a very small amount of energy is enough to move these electrons into the conduction band, and then they're free to move and carry electricity. Instead of this detailed picture, we will show the situation like this. After an electron moves from an overall neutral atom, it is left with 1 positive charge because 1 negative charge has left, 1 negative electron charge. Therefore, the rest of the atom becomes positively charged. So we show this by this. And the circle around this, it means that the charge is bound. It is not available, it's not mobile, it's not available to conduct electricity. But it has contributed an electron to the structure which is available to conduct electricity. So you're going to see plenty of electrons, roughly at room temperature, 1 corresponding to each of the donor atoms. And you will see a few holes as well, because holes continue to be generated using the process, through the process I described on the previous slide. We have many more electrons than holes, and for this reason, the electrons are called the majority carriers, and the holes are called the minority carriers. The number of electrons at equilibrium is approximately equal to the number of donor atoms, because as I said already, each atom contributes 1 electron to the structure at room temperature. 0 here stands for equilibrium. ND is the concentration of donor atoms, measured in atoms per cubic centimeter, or atoms times centimeter to the -3, or simply in centimeters to the -3. The product of electron and hole concentrations is still the same as before, Ni squared. And roughly the reason for that is the following. Because you have many more electrons now, there is a higher probability that a hole will encounter an electron and the two will neutralize each other. So therefore, because of the large population of electrons, many holes are neutralized and you end up with few holes and many electrons, but the product remains the same like this. So from these two equations, we can find the hole concentration, and it is given approximately by this formula. And this assumes, of course, that every donor atom has been ionized and has contributed 1 electron to the structure. And this approximation holds at room temperature. The opposite type of impurities are the so-called acceptors. For example, boron, gallium, or indium. These have 3 valence electrons. So, for example, here you have 1, 2, 3 valence electrons. They form bonds with the rest of the structure, and 1 electron is missing. That is already a hole. And as we have indicated before, the hole is free to move. The energy band diagram for this type of impurity looks like this. As you can see, this level, E sub A, is only slightly above the top of the valence band, E sub V. So it is now easy for an electron in the valence band to move to E sub A, fill the missing hole in that particular atom, but it now creates a hole in another neighboring atom where the electron came from, and now the hole is free to move in the valence band, just like free electrons are free to move in the conduction band. We will represent this picture like this. Because this was overall neutral, after the hole moved, in other words, it was filled, let's say, by an electron coming from another bond here, this becomes negatively charged. So we show these atoms are negatively charged. Each of them contributes a hole, like this. And there will also be few free electrons in the structure because they keep being generated through the process we described in association with the intrinsic semiconductor. In this case, we have many more holes than electrons, and for this reason, the holes are called the majority carriers and the electrons the minority carriers. As before, we assume that all of the atoms are ionized at room temperature, so the equilibrium concentration of holes is approximately the same as the concentration of acceptors. The product of N and P still is Ni squared for the reason I mentioned before, and from these two, you can find the concentration of electrons at equilibrium. And N sub A is the acceptor concentration. So in this video, we have talked about intrinsic semiconductors and extrinsic semiconductors. We have discussed holes and electrons in this case, and we emphasize that when we say electrons, we mean free electrons that are available to move. When we say holes, it's a more complicated concept. In fact, it's difficult to develop rigorously. It can be done with a given background, but for us, holes are basically carriers that carry a positive charge and can move, just as electrons carry a negative charge and can move. We will continue our review of basic semiconductor concepts in the next video.